What's up, lovely people? This is Medicosis Perfectionis, where medicine makes perfect sense. Let's continue my physiology playlist. In previous videos, we have talked about the structure of the muscles. We have talked about the actin, myosin, troponin, tropomyosin, the neuromuscular junction, and the excitation-contraction coupling. Today, we'll talk about muscle contraction, the difference between isometric and isotonic contractions, and the difference between SlowTwitch fibers and FastTwitch fibers. With that said, now let's get started. Please watch my physiology videos in order, otherwise there is no hope for you. Today's video is video number 54 in the series. Medicosis hierarchy of muscles. Your body has about 640 skeletal muscles. Each muscle is made of muscle fibers. Each fiber is made of myofibrils. Each fibril is made of myofilaments, which include actin, which is thin, myosin, which is thick. Each muscle is made of fascicles, which is a bundle of muscle fibers. Each bundle is made of individual muscle fibers or muscle cells, which are multinucleated in cases of skeletal muscles. Each muscle fiber is made of fibrils, which is made of filaments. What kind of filaments? Thick myosin and thin actin. From a Z line to the next Z line is a sarcomere. Let's say that I contracted. Alright, your sarcomere will shorten. The fibril will get shorter, the muscle fiber will get shorter, the entire muscle will get shorter. I've told you about this before. Everything here is about isotonic contraction, when the muscle gets shorter, but the tone stays the same. The word iso means the same. So when I say isotonic, what does that mean? Tonic, that's the tone of the muscle. Iso means the same. The tone of the muscle is not going to change. What's gonna change then? The length of the muscle. The length of the muscle will actually shorten. What do you mean? It means I'll bring the insertion closer to the origin. You have three types of muscles: skeletal, cardiac, smooth, and we have compared among them before. Let's review the excitation-contraction coupling. First, sodium influx to the neuron, causing depolarization, then propagation of the action potential, and then calcium efflux, and then rupture of the vesicle, exocytosis, acetylcholine is out. Acetylcholine is going to bind to the nicotinic sub-M receptor on the skeletal muscle, and then the action potential is going to move on the sarcolemma, and then it's going to enter into the muscle so that the T-tubules open the calcium channels, release calcium from its jail, first through the ryanodine receptor, and then through the L-type dihydropyridine calcium channel. And then calcium is in the T-tubule, is going to move until it reaches troponin C, and then troponin T is going to take tropomyosin and remove it away, exposing the active site on the actin. Myosin is going to bind actin, pew, pull it this way, contraction. Binding, bending, detachment, return. The functions of skeletal muscles were discussed before. Don't forget locomotion, posture, breathing, heat production. Now here are two stories, the story of medicosis and the story of a competitor to medicosis. Look at me, look at my shredded physique. I look like an ancient Egyptian god. Of course I'll be able to lift up this dumbbell, but look at my competitor. He just can't get it up. Medicosis has isotonic contraction. What does iso mean? The same, no change. Tonic, the tone. The tone of the muscle did not change. What changed is the length. And here the length has shortened. Translation, the biceps has shortened, which means the insertion is getting closer to the origin. My competitor cannot lift up the dumbbell. He's experiencing isometric contraction. What does iso mean? The same. Metric, length. The length of his muscle did not shorten because he could not lift it up. However, the tone of his muscle is increasing. His muscle is getting more tense, but he couldn't get it up. To illustrate the difference between isometric and isotonic, consider this example. So here is just a load, and we're trying to elevate that load, lift it. In isometric, what happened? Iso, the same, metric, length. The length did not change. Were we able to lift the load? The answer is no, because it's isometric. However, what happened to the tone? The tone increased. Look at this. Here at the beginning, it was like that. Not stretched, but here, the string is so stretched. How about isotonic, which is medicosis with his shredded physique? Yes, I was able to actually lift it. Did your tone increase? No, it's isotonic, and that's why I am not stretched. This part is called the contractile elements. Think of this as actin and myosin, and this spring is called series elastic elements. Whether it's isometric or isotonic, there is some sliding of the contractile element. Isotonic versus isometric. Isotonic. Oh, the tone did not change. Okay, so the tension did not change. How about the length? The length has shortened. That's medicosis story. Isometric. Isometric. The length did not change, but the tension increased. I can't. The contractile elements have shortened in each scenario, but the sliding of the myofibrils was more significant in case of isotonic than in case of isometric. Look at all of the sliding. It's getting closer to the myosin. Let's look at the elastic elements. All right, which one was more stretched? The isometric. Let's talk about work. Do you remember physics? Yeah, work equals force times distance. Since medicosis was actually able to move the dumbbell, the distance is there. It exists. That's why work is performed. But in isometric, there is no external work performed. Next, mechanical efficiency, which happens to equal the work in the numerator over the energy input in the denominator. Since there was no external work in isometric, the mechanical efficiency is 0. If you put 0 in the numerator, the ratio will be 0. Duh! But since there was some work performed in isotonic, the mechanical efficiency actually exists. It's not 100%, it's 20 to 25%. What happened to the rest of the energy? It has been released as heat. Time. Which one takes more time? Medicosis, who is actually successful at lifting it, or the person who couldn't? Of course, it takes more time for medicosis for two reasons. Medicosis has to overcome inertia and gravity. And more importantly, even though medicosis was able to lift up the dumbbell, he started as isometric, and then medicosis was able to lift it, so the isometric changed into isotonic. That's why it takes longer than the isometric. Energy. If it takes longer, it takes more energy because I have to overcome inertia. I actually lifted up the stinking dumbbell. How do you measure the force of contraction? If it's talking about isotonic, there is a device called SMT, or strength of muscle tension. Basically, we're measuring the velocity and the degree of contraction. So you're measuring the degree of contraction? Yeah, because I actually shortened. But in isometric, since I did not shorten, I can only measure the tension. And we use something called the electronic transducer for that. Can you give me an example of isotonic contraction? Sure, contraction of the biceps of medicosis to lift up the weight. And what's the function of that? Movement of part of the body or the whole body and lifting weights. Example of isometric contraction is the contraction of the quadriceps to stiffen and stabilize the knee joint. Let me give you an example. Let's say that Adam was standing on both legs, and then he lifted up his right leg. He's now standing only on his left leg. The question is, did the length of the muscle shorten? No, Adam did not get shorter just by lifting up his right leg. All right, Adam's height did not change. What changed is the tension. The tension on the left quadriceps and hamstrings has increased. You can actually do this. So touch your left leg and then lift up the right leg while continuing to touch the left leg. You will feel your muscles stiffening and getting more tense as you do this, because this is isometric contraction. No change in length, but the tension is increasing. There is a lovely game that you can play. Basically, they give you something like this that you will never be able to actually pull. So it's isometric contraction because you will never be able to pull it. And then there is a device to measure the tension. And this is basically will tell you who is stronger, you or your buddies. This device is called electrical transducer. It has transformed mechanical energy into electrical energy. A doofus might ask, the mechanical efficiency of these muscles is dismal. Look at the isometric contraction, 0 mechanical efficiency. Isotonic contraction, just 20 to 25. The rest is wasted as heat. I can make a robot that's more efficient than that. This is just so sad. The human body is bad. Shut up. Let me tell you, the concept of mechanical efficiency or work over energy can be very misleading, and I learned this from my hero, Dr. Thomas Sowell. Let me explain. Suppose that we have two guys living in Alberta, Canada in the winter. It is brutal up there. Too much snow, too much ice. And we have two men trying to get to work on time. The first person has a car with traditional light bulbs, not so efficient. The second person has LED bulbs, which are way more efficient. What do you mean by efficient? I mean mechanically efficient. I mean the vast majority of the energy is being used to actually emit light, giving you an efficiency of about 99% or something. But the traditional light bulb will waste too much energy in form of heat, giving it an efficiency of, let's say, 80%. Okay, so from the standpoint of a woke engineer who cares only about mechanical efficiency while living thousands of kilometers away, the second car is better. But from the standpoint of the Canadian driver who needs to get to work on time and needs those light bulbs to actually emit a lot of heat to melt the snow so that he can see better, so that other drivers can see him better to decrease the risks of accidents. Moreover, if the headlight is not emitting so much heat, he will have to clean and remove the ice from the headlight himself, which takes time. Time is money. He's gonna be late to work. If he has to clean the snow himself, this will increase his risk of frostbite and cold agglutinin disease. I have a video about cold agglutinin disease in my hematology playlist. But the moral of the story is, from the standpoint of an engineer who cares only about mechanical efficiency, car B is better. From the standpoint of the actual driver who has to drive the car in Canada where it's cold, the traditional light bulbs are better. Even though they are not so efficient? Yes, doofus, even though they are not so efficient. If you define efficiency as mechanical efficiency, car B wins. If you define it as getting to work on time while wasting less time and energy clearing the snow, car A is better. By the same token, if you think the only purpose of your muscle is to bring the insertion closer to the origin, then your muscles have failed you with a dismal 20% mechanical efficiency. But if you think that the purpose of the muscle is not just locomotion, but also to maintain the body posture and to produce enough heat so that you do not die from extreme cold and so that your internal body temperature is kept at about 37 degrees Celsius, which is an optimum temperature for all of the enzymes in your body. All of these enzymes are proteins. Then your muscles are not failures. Your muscles are actually awesome. But I can make a robot that's more efficient. Can your robot heal and self-regenerate? No. Then shut up. Can your robot synthesize proteins? No. Shut up. Why do you think the GOAT, Lionel Messi, warms up and stretches before the match? Do you think he's stupid? Nope. Do you think he's wasting his energy in form of heat? Also no. He's trying to raise the temperature of the muscle to make it easier for the actin and myosin to slide over each other. So mechanical efficiency is a sound concept, but it's not the only game in town. You still have to maintain posture. You still have to produce heat for your body. A similar doofus might say, the body is so bad because the shoulder joint is easily dislocated. That's true. You know why? Because in the shoulder joint, we have sacrificed stability for the sake of a wide, robust range of motion. If you want a joint with more stability, it exists. It's called the hip joint. So it's not about good or bad. It's about choices and trade-offs. Because there are no solutions in life, only incremental trade-offs. Form follows function. Quick question, can we have both isotonic and isometric contraction at the same time? The answer is yes. Let's say you're running. This left leg has to maintain your body posture. Isometric contraction. You are bending the knee right here. That's isotonic. You're shortening the muscle. Isotonic here as well. So yeah, you can have both. In case of isotonic contraction, we are measuring the shortened length. In isometric contraction, we are measuring the tension. So let's have some graphs. Isotonic, the tone did not change, so I will measure what the distance shortened. Okay, you give action potential and wait, and then boom, contraction will happen. Electricity before the light. Action potential before the contraction, and then you measure the distance shortened. Cool. Isometric is different. The length did not change. What changes is the tension. So you plot the tension against time, and boom, the tension is increasing. What would you call the period between giving an action potential and the actual contraction? I'll call this the latent period. What would you call the period between salmonella getting into your body and the development of symptoms, latent period. What's the contraction time? It's the time between the start of contraction and the peak. Now take a deep breath. What are the factors affecting skeletal muscle contractions? Many factors, including the type of muscle. Are we talking about the slow twitch, red or type 1 fibers, or are we talking about fast twitch, the pale or type 2 fibers? The difference between type 1 and type 2 muscles is like the difference between the ox and the chicken. Let's start with the ox. Okay, ox, tell me about yourself. All right, my muscle fibers are small. Look at this. Look at my teeny tiny legs. They contract slowly. I have to move slowly while pulling on this mill. But look, even though they contract slowly, they are highly resistant to fatigue. I can keep spinning the mill for hours without getting tired. Enter the chicken with her fast twitch or pale or type 2 muscle fibers. My muscle fibers are large. My chicken breast is delicious and thick. My muscles contract very rapidly. You can look at me flapping my wings so fast. However, I get tired very quickly. Does my body have slow twitch fibers or fast twitch fibers? The answer is your body has both. Not just that, even one muscle, the gastrocnemius, can have both types of fibers at the same time, fast twitch and slow twitch. Let's compare between type 1 and type 2 muscles. If you remember the ox versus the chicken, everything is going to be easy. Muscle fiber size, small, large. Innervation, small fibers by small, slow nerves, large fibers by large motor neurons. Why are red muscles red? More mitochondria, they are red. More myoglobin, that's red. More blood supply. What's the purpose of mitochondria? Oxidative phosphorylation. We're talking about oxygen here. Myoglobin, it's an oxygen binding protein. More blood supply will give me more oxygen. The key word here is aerobic. Oxidation, baby. But in type 2 fibers, there is less mitochondria. That's why the chicken is pale. Less myoglobin, not red. Less blood supply, pale. If you don't have mitochondria, you will have to go to what? Glycolysis. That's the only game in town. Remember your mature red blood cells? Yeah, they do not have mitochondria. That's why they only have glycolysis. Do they have Krebs or TCA cycle? No. Do they have an electron transport chain with oxidative phosphorylation? Also no. That's why the keyword here is glycolytic, not oxidative, and this is anaerobic, not aerobic. The myosin ATPase activity is low in case of type 1, high with extensive sarcoplasmic reticulum leading to rapid release of calcium, and that's why these are fast twitch, but they get tired easily. Slow, fast, resistant to fatigue is high, but the fast twitch fibers will get tired easily. Can you give me examples? Sure. Slow twitch include your back muscles. The back is carrying your weight, especially the weight of your head. Your head is so heavy. If you wake up at 8 a.m., do you think your back muscles are going to get tired by 10 a.m.? Shut up. They are very resistant to fatigue. Same thing with the soleus muscle and gastrocnemius muscle. They are carrying the entire body weight and they do not get tired easily. Fast twitch fibers include hand muscles and extraocular muscles. Eye muscle strain is a common problem, especially if you're staring at your smartphone the whole day. Other textbooks will classify the muscles into type 1, type 2A, and type 2B. I don't care. So we have talked about the types of muscles. Let's talk about muscle fatigue. And we will continue 2, 3, and 4 in the next video. Muscle fatigue. Prolonged contraction or strong contractions eventually lead to muscle fatigue. You'll get tired. What's that? The contraction strength is decreasing. The duration of contraction is increasing. It takes me longer to lift the dumbbell, and the relaxation becomes incomplete, leading to contracture. Why do muscles get tired? Accumulation, depletion, interruption, transmission. Accumulation of lactic acid, depletion of muscle ATP, of glycogen, of creatine kinase, etc. Interruption of blood flow, decreasing oxygen, and decreasing transmission at the neuromuscular junction because this also has fatigue, if you remember my previous video. Quiz time. Alright, question 21. Medicosis was given 3 loads, load A, B, and C with different weights in order for me to try to lift them, try to match. So, one of these loads is light, one is heavy, one is intermediate, and this is A, B, and C. Please try to match. Let me know the answer in the comment section. You'll find the correct answer in the next video. Do you remember question 20? You have 2 autoimmune diseases. What's the name of A, which attacks your calcium channels? It's called Lambert-Eaton myasthenic syndrome. B is myasthenia. Let's review Lambert-Eaton from Picmonic. Lambert-Eaton, here's the lamb, Eaton. What's the problem? Antibodies, here's the antibody attacking the calcium cow channel. This will lead to decreased release of acetylcholine, acetylcholine. Lambert-Eaton myasthenic syndrome is probably a paraneoplastic syndrome. Here's a cancer cell, and it's associated with small cell lung cancer, also known as oat cell carcinoma. Lambert-Eaton myasthenic syndrome has proximal muscle weakness, not distal, proximal. The more you contract your muscles, the better it gets. You'll get less tired, and this is very different from myasthenia gravis. In myasthenia, the more you move your muscles, the more tired you get. Lambert-Eaton myasthenic syndrome has autonomic symptoms, such as urinary bladder problems. However, the extraocular muscles are spared, and this is different from myasthenia gravis, because in myasthenia gravis, there are many eye symptoms, but the eye extraocular muscles are fine in cases of Lambert-Eaton myasthenic syndrome. If you want to learn about physostigmine, neostigmine, and their use in myasthenia gravis, as well as rivastigmine, galantamine, and their use in Alzheimer's disease, check out my autonomic pharmacology course on my website, medicosisperfectionis.com. I also have a cardiac pharmacology course and an endocrine pharmacology course. Thank you for watching. Please subscribe, hit the bell, and click on the join button. You can support me here or here. Go to my website to download my courses. Go to Picmonic for animated medical mnemonic. Thank you for watching. Be safe, stay happy, study hard. This is Medicosis Perfectionis, where medicine makes perfect sense.